in case anyone had a doubt. Yeah. Okay. Welcome everyone to another DevMap seminar. So it's my great pleasure to introduce Gramoz Goranci, who's a speaker today. Gramoz did his PhD from Uni Vienna, and after a postdoc at University of Toronto, he is shortly going to be a UK colleague of ours, joining University of Glasgow. So Gramoz has made several outstanding contributions to dynamic graph algorithms, and today he's going to tell us about the dynamic maintenance of low-stress probabilistic tree embeddings with some applications. So Gramoz, whenever you're ready, over to you.
Thanks very much, Roman and John, for the introduction and for the nice words. And I also want to thank Simon for inviting me to the seminar. And this is joint work with Sebastian Forster at the University of Salzburg and my former advisor, Monika Hensinger. Okay, so let's look at this widespread idea in graph algorithms. So let's assume I'm given a graph G and I would like to solve a problem on this graph, say some optimization problem. So now many problems are hard to solve in graphs because graphs can have very complicated structures and we don't really understand them. But there's one exception. If the underlying graph is as simple as a tree, then usually many problems become much easier to solve on trees. Many graph problems become much easier to solve on trees. So the hope is that can you take this complicated graph that you don't really understand and approximate it by some tree structure such that this tree structure preserves the objective function you're looking at from the optimization problem. And can you do that first? And after doing that, can you translate the solution that you solve in this tree instance back to the original graph, right? And this idea has been used quite a lot in the design of graph algorithms. For example, if you are interested in preserving property like connectivity, then you can simply compute a spanning tree or forest in the graph, and it is known that this exactly preserves connectivity. If you want to preserve the shortest path distance between a source vertex to everyone else in the network, then you can basically take a BFS tree or a shortest path tree. If you want to preserve pairwise ST max flow min cuts, you have Gomery-Hood trees. If you want to preserve multi-commodity flow structure of graphs, you have tree and cut and flow sparsifiers. And today I'm going to talk more about trees that preserve distances. And one canonical example is the low average spanning tree, which preserves pairwise distance on average. But today I'm going to talk about the randomized version of this, which is called a probabilistic low-stress tree. And this tree preserves pairwise distance in the graph in expectation. So let me be a bit more precise what a probabilistic low-stress tree is. So I'm given a graph G, and for simplicity, let's assume that this graph is unweighted. By n, I denote the number of nodes, and by m, the number of edges. And the goal is to construct a probability distribution over trees with the following properties. So each tree in this probability distribution must contain the vertices of the original graph as leaves here. But it may contain also additional vertices, which I'll call Steiner vertices, okay? These blue vertices over here. So this is the first property. The second property is that the distances in each tree in this probability distribution dominate the distances in G. Okay, so they are larger. And the third property is that if I sample a tree from this probability distribution, then in expectation, I get that the distance in one of these trees is not like far away from the original distance in G. And so how do I measure this, how far away I am from the distance in G? By this approximation factor alpha, which is greater than 1. Obviously, the goal here is to find an alpha probabilistic tree embedding, which is abbreviated usually as an alpha PTE with a small alpha. And this alpha, this approximation factor alpha, is usually referred to as stretch. By how much am I stretching distances by going from G to a random tree. And this has been a very powerful tool in approximation algorithms. Many problems benefit from this paradigm, including bulk network design, group Steiner tree, metric labeling, oblivious routing, min-sum clustering, distributed case server, and so on. Today, I'm going to talk mainly about the Bayes bulk network design application of this probabilistic tree embedding and the approximate all pair shortest path. So these are the problems that I'm mainly going to focus on and the applications of the PTEs. Okay. So before I tell you what is known about approximating graphs by trees such that the distances are preserved in expectation, let's have a look at the simplest graph instance, which is not a tree, and this is simply a cycle. Okay, a cycle on m vertices. So first, you can say, what about like just having a single tree that approximates distances? So even in a cycle where you just can delete anything, any edge, and then get a tree, like a spanning tree, right? You can delete any of these edges that get a spanning tree. It's known that the stretch must be at least, deterministically, the stretch must be at least n-1, right? Because if I delete this edge, then I have to travel n-1 between these two endpoints, right? In fact, in 95, Rabinovich and Ratz showed that any tree, if you take any tree, so if I even allow additional Steiner vertices here, you cannot approximate the n cycle better than some asymptotically better than n, okay? So even if you allow more structure, more vertices in the tree, nothing can be done. So, and this leads to the obvious question, oh, can we do this with random tree, right? And Richard Karp in 89, so obviously in a slightly different application, he was interested in the case server problem. It showed that actually for the n cycle, you have a very easy to PTE algorithm, okay? So what is this algorithm? I just go and look at all edges in the graph, and I delete one with, just delete one at random, okay? So probability 1 over the number of edges, which is n in the cycle. So let's look at the analysis of this. Why is this good? Why is this a good probability tree embedding? So this is like the one-line analysis of this observation. If you delete an edge, then this edge is stretched a lot, as you see here, right? But what's the probability of edge being deleted? Is just 1 over n, right? So if you basically delete this edge, then you're going to pay n-1, which is this one. This is the stretch. But if you don't delete the edge, and this happens with, you see, very high probability, then the stretch remains the same. So basically, if you bring these two together, you just get 2 times the original distance. And of course, this holds for the edges, but by linearity of expectation, it holds for any pair of vertices here. Okay, so this is fairly simple. So what about general graphs? So for general graphs, Bartal in 96 showed that you can get log square stretch for probabilistic tree embedding. And he also improved this result in 98 by showing a log n log n guarantee. And then there's this seminal work, which is usually known as the FRT result. The first name, it's hard for me to pronounce, but then it's this guy, and then Rao and Talvar. So they show basically an asymptotically tight upper bound of log n. And then people were interested, oh, can we do this faster? What about the running time now that we know that the stretch is tight? And they Mendel and Schwab observed that you can do m log to the 3n. And then finally, you can also, there is a recent result by Blelo, Ga, and Sun, who can do essentially like m log n time and log n expected stretch for probabilistic tree embeddings. We also know that on expander graphs, you cannot do better than log n. So essentially, everything here is sort of like tight, maybe up to some log factors. I'm not sure if you have to pay this log factor in the running time, but this is tight asymptotically. Okay. So in this talk, we look at the dynamic version of the problem, okay? So what does this mean? So I'm given a graph G, and I have an adversary which inserts and deletes edges. This is an online problem. So the goal is to come up with a data structure that can process these updates. So can process deletions of edges, for example, these edges over here, and also insertions of edges, okay? And at the same time, this algorithm must be able to maintain a random tree T such that tree has competitive stretch. Okay, and I will briefly explain what do I mean by that. And also the algorithm can also add and remove edges to T. So it has the freedom to do things, but at any point of time, we must have data structure access to the tree T. Okay, and this the stretch of this tree must be competitive. And by competitive, I mean something polylog or subpolynomial. So what is the goal here? The goal is to minimize update time, and this is the time to handle edges, insertions, and deletions in the graph G. So note that the very simple algorithm is like whenever I have a change in the graph G, I just recompute everything from scratch, right? So this is very expensive, and ideally would like to do something better than recomputation from scratch. Okay, so this is the problem we are looking at. So what do we achieve for this problem? So we show the first dynamic algorithm for maintaining probabilistic tree embeddings, and we can do this obviously in sublinear time. And I would like to talk a bit about the specifics of our results. First, our bonds are amortized. So by amortized, I mean here that when I have an update, it might be very expensive, but over a sequence of updates, I should be fine. Okay, I should be competitive. And we also assume oblivious adversary. So we assume that the sequence of updates is fixed in advance. It doesn't have access to the random bits that the algorithm does. So these are sort of like limitations, which are somewhat standard in dynamic algorithms, but we would like to, of course, like get worst case guarantees and adaptive adversary, but we don't have that yet. And on the positive end, we show that we can handle graphs with polynomially bounded ways. So this result doesn't hold only for unweighted simple graphs, but it holds for graphs with polynomially bounded ways, which is an upside. So let's look at the spectrum of the results that we get for dynamic PTE. For example, in one extreme, we get a stretch which is polylogarithmic, and the update time is square root of m. M is the number of edges in the current graph. On the other extreme, we also get subpolynomial stretch and subpolynomial update time. And more generally, we get this trade-off between the stretch and update time. And this is, for example, we get a log n to the 3 I minus 2 and m to the 1 over I plus the 1. And I is at most square root of log n. We know this as a consequence of the hierarchy that we maintain. So if we set I to be fairly high, then this is a very competitive update time. So it can be a very small polynomial. And we still ensure that the stretch is basically polylogarithmic. Okay. So let's try to compare this result to some related previous work on similar type of problems. There is this problem of which is called the low average spanning tree, and there are like recent dynamic algorithms for low average spanning trees. There, the best known result is subpolynomial stretch and subpolynomial update time. And this is by Chechik and Zhang. It's Soda 2020. And the stress type there is average. What do I mean by average? So I have only a single tree. I don't have a probability distribution over trees as in our case. I have only a single tree T. And I look at the how much are my edges stretched in the tree T, and then I take the total stretch of all the edges divided by the number of edges. This is the average stretch guarantee, and this is a single tree. So the upside of this result is that this is a spanning tree. Our result is not a spanning tree; it's just a low depth tree. Okay. But these two are not comparable in this sense. So they're sort of like related if we talk about these problems in the static setting, but not in the dynamic setting. And moreover, for example, for the low average stress spanning trees, we don't know any algorithmic application besides the fact that it's an important object to look at in the dynamic setting. But for dynamic PTE, we will show algorithmic applications like maintaining all pair shortest path and other approximation algorithms. Okay. But I'm happy to talk more about this if someone has question about the differences between these two results. Before I tell you what we achieve for our application, let me briefly introduce the Bayes bulk network design problem for those that haven't seen this before. So here the idea is that I'm given a graph G and I have some positive lengths on the edges. I'm also given some demands among pairs of vertices, like a source and a sink is ITI, and the number of these demands is K. And finally, I'm also given a subadditive function F, which is non-decreasing. And this subadditive function models what is the cost of purchasing an edge in the network. And it's subadditive because it's cheaper to buy, for example, 2 quantities than buying these quantities individually. That's what this subadditive function means. So before I tell you the objective of the problem, let me tell you what routing and the edge cost entails. So routing is just some routing. So basically constructing a collection of paths for routing demands for these source sinks pairs. And this path that we construct send this sort of like you can think of as unit of flow. So the amount of demand you set from SI to TI. And so just basically like for every pair SI-TI, I need to construct paths and I send this amount of demand or commodity among the endpoints of this path, right? And naturally you look at the cost of an edge. And what is the cost of an edge? Is the amount of flow or commodity you send along the edge. For example, you see that for connecting these pairs here in the picture, this edge has been used twice. So the cost of this edge is twice, right? You can also think this is the congestion of an edge. Okay, and this so this tells you how much capacity do I need to buy so that I can route all these flows feasibly in the network, right? So you are not given the capacities. This is like a typical problem in network design. So you like to find out what are the cheapest way of buying capacity so that I can route my flows feasibly. Okay. And now, obviously, when you talk about these things, you want to minimize some objective functions, and we like to find a routing PI that minimizes the total cost. And the total cost is defined as you look at the cost of an edge. You basically the cost of an edge is F of CE. This was the so like F tells you like how expensive it is to buy an edge, and this is estimated with respect to this subadditive function F. And you multiply this quantity by LE, and then you sum over all E's. This gives you the total cost. Okay, so this is the byte-bulk network design problem. So let me now tell you about the applications of dynamic PTE. So our first application is the fully dynamic all pair shortest path problem. So in this problem, this is one of the most classical problems in the design of dynamic algorithms. And here I'm just talking about a very specific setting, which is fully dynamic version, and I'm allowing approximation larger than 1. So if you allow different versions, then you will have a bunch of other results. But here I'm just talking what is relevant to this work. So for this problem, for fully dynamic all pair shortest path problems, where the underlying graph is changing with the edge insertions and deletions, we obtain the following result. We can show, so one thing that I should just point out here is that these guarantees just follow from the probabilistic PTE. And in the query time, we get some log n over hets, which I will describe later. So basically, we get very good polylogarithmic approximation to the shortest path in the network, and the update time is some small polynomial. Okay. And comparing our result to the previous work, we should mention that this goes beyond the square root of m bound on the update time with non-trivial approximation by Abraham et al. Because in their guarantee here, regardless of how you choose k and rho, you cannot go beyond this, the square root of m bound. So we show that you can go beyond the square root of m bound by still maintaining competitive stretch. Okay, so this is the high-level message of our dynamic PTE. So for the fully dynamic byte-bulk network design problem, which I briefly introduced in the previous slide, for this, we similarly get the same guarantees. And moreover, we also allow that the demand pairs are given to you online. So the graph undergoes edge insertion and deletions. On top of that, you can also give the demand pairs online, and you just pay proportional to the number of demand pairs you have. So if this is small, the recurring time is very competitive. So you don't need to know that in advance. Okay, so it's like even more powerful here. And this is the first dynamic algorithm for the problem. We know in the static setting that you have to pay some logarithmic approximation for byte bulk. So this is tied up to polylogarithmic factor. Of course, it's interesting if you can do log, but we are not there yet. Okay, so these are like some of the immediate applications of dynamic PTEs. Okay, so let's start explaining a bit about how we get these things. And we first look at the deletions only problem, which is widely known in the dynamic community as the decremental version of the problem. Here, I'm interested in the same exact problem, but I'm not allowing insertions, okay? My graph is only undergoing deletions. So how do we obtain this result, the decremental PTE? So this builds upon the decremental LDD, which is decremental low diameter decomposition. And I will briefly tell you what the LDD is in the next couple of slides. And this in turn is based on pruning approach. It's based on decremental single source shortest path and also dynamic bulk growing. Okay, so for getting this decremental LDD, we need all these three techniques and sort of like white box them and like be careful in keeping track of everything. Once we have this, we can have an iterative version of top-down clustering by Bartal, and you will see that you will get the decremental PTE algorithm. So for getting the fully dynamic one, we introduced a new bootstrapping idea, which is sort of standard in dynamic, but here we have this subtle difference that we recursively employ fully dynamic algorithms in the reduction instead of like employing static algorithms when we do the bootstrapping. But you will see details. So this is the overview of the talk, of the technical part of the talk. Okay, so let's start about telling you something about clustering in graphs. And I want to, so the whole idea is that I'm given a graph G. I want to partition the graph into clusters of small diameter. And at the same time, I want that each cluster has so the number of intercluster edges between these small diameter components is sort of small, okay? And there are different variants of this, but what is helpful for us is this probabilistic version of clustering, and which is called the beta gamma LDD. And so here the idea is that I want to have a randomized partitioning of G into vertex disjoint clusters C1 to Ck such that the following properties hold. Okay, so by randomized partitioning, I mean like a probability distribution over these vertex disjoint clusters. So the first property is that the weak diameter of each CI is at most beta. So what do I mean by weak diameter? Okay, so this is a bit tricky, but it's important to understand. So if I talk about strong diameter, then I mean that if I look at any pair of vertices in this cluster over here, the distance, the induced distance in this cluster is at most beta, okay? But the weak diameter says that basically you can use edges outside the cluster. So you can use edges in the graph G, and then that is at most beta, okay? So the weak diameter is like, of course, like a weaker notion than the strong diameter. And any strong diameter is a weak diameter, but not vice versa, right? Okay, so this is important. And the second property is that the probability that an edge is an intercluster edge is at most gamma. Okay, so what does it mean to be an intercluster edge? What is the probability that one endpoint is contained here and one is contained in another cluster? This is at most gamma. Okay, so this is the definition of a probabilistic LDD, and this is a tool that has been used, or I could actually say that you can find in basically all tree-based graph approximation construction for distances. For example, if you want to construct low-stress spanning trees or probabilistic tree embeddings. And also in approximation algorithms, there you can see many applications of low diameter decomposition for example, studying min-max graph partitioning and so on. So it's a very powerful tool in algorithm design. So now we look at this decremental version of the problem, okay? So what is the goal here? Let's try to understand the goal here. So the goal is to maintain this beta gamma probabilistic LDD as the underlying graph G undergoes edge insertion, edge deletions, right? No insertions here. So now you see these clusters over here, and so some of the edges actually might be deleted. So you would like that you still have a good clustering, right? But good clustering means like you maintain this property that the weak diameter is small and the intercluster probability is also small, okay? So this is sort of like the main result that we show in the paper. We show that for any beta between 0 and 1, so you can think of this as a reduction parameter. So there is a data structure for maintaining a beta to the -1 log squared m probabilistic of the d of g in almost linear time. Okay, so you see there is this tension between the intercluster probability and the diameter you're interested in. And you can do this in m to the plus little 1 total update time. So by total, I mean like over the sequence of all deletions. So if I divide this by m, the amortized update time is going to be just m to the little 1, right? Or like subpolynomial. And I should emphasize also that this is tied up to a log factor here. So it's known in the static setting, you cannot do better than beta to the -1 log n. So here, like our guarantee is tied up to a log factor here. So this is what we achieve. And so why is this result interesting? Well, I will tell you a few technical things why actually this is needed for what we're trying to do. So I want to mention that our running time is independent of beta to the -1. Okay, you don't see any beta factor here. Why is this important? So this is a key requirement if you want to do top-down graph clustering for constructing probabilistic tree embeddings. And sorry, this is no. Well, let me see. Oh yeah. So yeah, no, this is okay. So if beta, so what does this mean? So this beta usually, when you do top-down clustering, is invoked with being something proportional to 1 over diameter of G. Okay, so if I had dependency on this beta -1, then I would have to pay some running time, which could be as large as mn, right? And I don't want to do that because then I'm not getting any sublinear algorithm there. So this just defeats the purpose of getting efficient dynamic algorithms. Okay, so this is very important that we can achieve this. So our running time is independent of this reduction parameter. This appears here, obviously, but not in the running time. So I also should mention that all previous dynamic graph clustering algorithms, the expander decomposition based, which gives you low stretch diameter clusters by Saranrak and Wang. And then you have also Chechik and also previous work of mine with Sebastian. These all algorithms have actually dependency on beta -1. So ours doesn't. So, and it's important for doing this top-down graph clustering. Okay, so let's start by looking at the static probabilistic LDD, and then I will try to explain you how do we make this dynamic. So this is a very simple ball growing argument. So initially, I have a counter which is set to 1, and every vertex initially is unmarked. Okay. So now, while there are unmarked or unvisited vertices in the graph G, I just pick an unmarked vertex V, an arbitrary vertex. I sample a radius from the geometric distribution with some parameter P, and P is roughly b to the -1 log n. And I add all unmarked vertices in the ball that I grow with center V at distance, so with radius RV. Okay, this radius is from the geometric distribution, right? Like random variable. And I add all these unmarked vertices to this current cluster CI. I increase the counter. So with C1, C2, and so on. Okay, so this is what the algorithm does, just like ball growing and cuts at random probability. Okay, so it's not very hard to show that this ball growing construction gives you a beta to the -1 log n LDD in nillinear time. Okay, it's fairly easy to show this. I mean, once you see it, of course. And then the whole question is how to make this construction dynamic, because in the beginning it seems like there are sort of like this chain of independencies. You pick something, you grow a ball, then you pick something, grow a ball. So it seems like a very static process. At least for me, like initially when I started looking at the dynamic versions of this, I never thought that we could use something like this. Okay, so the whole idea is we white box and extend some cluster pruning technique of Chechik and Zhang. Okay, so now here's the moment where things get a bit technical. So I hope you're still with me. But yeah, I would like the whole idea is that I want to tell you how we do this cluster pruning. And in fact, it's very easy. But so let's see. So there are some technicalities, and I will try to convey the intuition why we need those. So initially, I just start. I have this graph G, like, and the vertex set V, right? So what I do is I first assign a random center to this graph. Okay, so this assigns center procedure. So I pick a random vertex proportional to the volume, okay, of the cluster. So degree over the volume. And I also initialize a two approximation decremental single source shortest path algorithm. So you can view this as like an approximate Dijkstra tree, okay, on this cluster C. And this is rooted at this cluster, at this center C, okay? So this is what I do in the beginning. And now, after I've done this random center assignment, the most important tool in our algorithm is this prune procedure, okay? So what pruning does is very intuitive. Okay, so it does the following. So let me look at the cluster C, right? C initially is V, and then it just gets smaller and smaller. So if the size of the cluster is non-trivial, right? And there exists a vertex that it's far away from its center, and we are interested in this diameter parameter, doesn't really matter, right? But it's very far away from its center. So what do we do? So what we do is sort of what we did also in the static version. So we sample a random variable from the geometric distribution, and we grow a ball with V being at center with radius R. Okay. So now here's the tricky part, which we will need to make this work in an efficient way. So if the volume of this cluster is at most half the volume of the original cluster, so now we're looking at this cluster B. This cluster B is this green cluster over here in the picture, right? So it turned out that this vertex was very far away from here, and then I was growing a ball around this, okay? So once so now I look, what is the volume of this ball with respect to the volume of the original ball, okay? If it's like just some constant fraction, what I do is I just delete this ball from the cluster. So just prune out this whole thing, right? This is why it's called pruning, because you prune out the whole thing from the cluster, right? And you introduce this new intercluster edges over here too. Okay, and so now you start a new process on this cluster B. So what do I mean by starting a new process? You assign a new center at random, right? And then you also prune the cluster recursively, okay? If this doesn't happen, if the volume of the ball is actually large compared to the initial volume, then you do some center reassignment. So you pick a new center in the graph. Okay, so this is an expensive step, and we will show that the center, I mean, I'll at least try to convey that the center, so the number of center reassignments is logarithmic. Otherwise, this would be very expensive, okay? And then we recursively prune the cluster again and so on. So that's pruning. So basically just, I would like to reiterate over this again and again, because it's the most important part of the algorithm. So I'm giving some cluster, and when I do pruning, I just look at whether there is a vertex that's far away from the center. And if this is the case, I grow some ball and I start a new like process on this this smaller ball, depending on that whether the volume is good in terms of like the original volume, right? And for handling deletions, I just do this. So I look at all clusters that this edge E is contained in, I just run prune on this. And like this makes sense because, for example, when you have an edge deletion inside the cluster, right, then it might be the case that these edges were used for some of the distances, like to guarantee that the cluster has small diameter. And by deleting this edge, you actually make the cluster not have a, so like make the cluster violate the diameter property, right? And that's why it's natural to look at like creating a new cluster and pruning out from the old cluster, from the parent cluster, if you want to think. So, and also it's kind of easy to see that by doing this pruning, you also establish sort of like a tree hierarchy relationship. Like your pink cluster is the parent cluster, and all these green cluster are a child cluster, and so on. So you kind of do this recursively. Okay. So what is important here now? So we look at this, what we call the dynamic ball growing process. And this process runs in different rounds here from I to k, and k is like some like positive number. And it has the following step. So the first step is I choose a vertex ci of this graph gi, and these are all balls that have been removed from the cluster so far, and all edges that have been deleted from the adversary, okay? And the second step is that I sample some random variable from the geometric distribution, and I grow a ball bi from ci with ranges ri and gi, okay? So this is the same as the static ball growing, but this is interleaved now with deleting balls from the cluster, like pruning out balls, the clusters B, and also deleting edges from the cluster. So what we show is that in fact you can get the following guarantees. You can get that this radius is bounded by p to the -1 log n, and this is just an artifact of that you just use this p. You sample this ri to be from the geometric distribution. So it's not hard to see that. And for any edge that remains in this ball, like growing ball, dynamic ball growing, the probability of this edge leaving the ball, so being an intercluster edge, is at most p. Okay, we can also show this. And you have to also understand here, so whenever a cluster is created in our dynamic pruning algorithm, so whenever we create a cluster here, we associate this dynamic ball growing, right? Because there might be, baby clusters being pruned off of these clusters and so on. So whenever, even so initially, my whole graph is a cluster, and then I'm gonna do it for like vertices that are happy, which induce other clusters and so on, okay? And you can see that because volume of this cluster B is at most half the volume of the original cluster C, right? So it's reduced by a constant fraction. You can charge each edge. So you can think of like each edge can participate in at most log n cluster during this dynamic procedure, okay? And this comes right away from this guarantee over here. And another assumption that we have here, and which is very important, is that the deleted edges E1 to EK, these are edges that are deleted from the adversary, they don't see the values R1 or otherwise they could just destroy our clusters. Okay, they don't have access to this sampled probabilities. Sorry, this is sampled radius. Okay. Okay, so this is just like a high level of a high level description and trying to give you a bit of like a glimpse of what's going on with our dynamic ball growing. Okay, so let me have yet another technical slide, and hopefully we'll be done after this and we'll be more high level. So I want to tell you a bit about the running time of our cluster pruning. So we know how to maintain decremental approximate single source shortest path tree. You can do this in you can get a 2 approximation. You can do this in almost linear total update time. Okay, this also assumes oblivious adversary. There are even recent works that assume adaptive, which actually simplify our algorithm. So another 2 properties that are very important are the following. So when we grow balls, you can view this as a local algorithm. So I just need to grow balls starting from the center, and then I take these larger and larger neighborhoods. And actually, I can compute this proportional to the volume of that ball times some log overhead. This means that I don't need to visit the whole cluster. I just need to visit volume B many edges, okay, when I do this ball growing. And another thing which I won't prove here because it's a bit technical, but it's very important, is that the total number of center reassignments is logarithmic. And so this is the center reassignment, right? When my ball is too large to be pruned off, I assign a new center in the ball growing process. Okay, so let's look briefly at the analysis. So let's look at the analysis from the perspective of cluster C. So now I can charge the running time to assign center C and prune C. And I won't talk about what is the time for maintaining B's here, right? Because B's have their own charging going on. So first, the runtime of assigned center is dominated by property 1, okay? And we know this is m to the 1 plus 1. Why is this the case? Because random sampling, I can do it efficiently. And the second step of the assigned center was just maintain a approximate single source shortest path algorithm. And this we can do in this time, right? Now, by 3, the total cost of assigned center is this, MC to 1 plus 1. M sub C, 1 to 1 plus 1. Why is this the case? Because, I have a small number of center reassignments. Now, by property B, because the volume, whenever I remove a ball, the volume has to be 1, so half of the volume of the original cluster. To each edge, I can charge this log m time, right? Because this just halves. And this is the running time for keeping track of all these ball growing. And also note that all these clusters that I'm actually building are disjoint. So, and then there are log n levels in this tree hierarchy induced by the ball growing. And then you just get the total update time to be m plus 1. So this is sort of the analysis and the idea, why do you get this m to 1 plus 1 total update time for maintaining decremental PTE. Okay, so let's talk about how to use decremental LDD to get a decremental probabilistic tree embedding. So let me first tell you briefly what is our result. So we are given a graph G, and this graph undergoes edge deletions, and we can maintain a random tree T. So we can sample sort of like efficiently from this probability distribution. This tree has height log n. The expected stretch is polylogarithmic, it's log to the 3n, and the total update times is m to the 1 plus 1. Okay, so what is the high-level idea here? We apply decremental LDD in a non-recursive way, and we use top-down graph cluster. Okay. So let's look at first a few attempts, like natural attempts of doing this. So one attempt is the following. So you're given this graph, right? And then you compute a probabilistic LDD. And for each of these probabilistic LDDs, you run a decremental algorithm on top of each of these, right? Then you contract everything into a single, you clump everything into a single vertex. And then you have another partition, right, on top of these two. These are single vertices, now these gray clusters. Now you have this other partition of the graph. In fact, this even gives you a spanning tree and so on, okay? With a problem with this approach that what is called a bottom-up clustering, it was used in the first construction of along Carpelec and West in 91, is that it just gives you n to the little 1 stretch. Okay, you cannot go and get polylogarithmic stretch with this construction. And also another downside of this is that it requires fully dynamic LDDs. So so far I showed you how to do decremental LDDs only under edge deletion. So this requires fully dynamic LDDs. So, and why? Because, for example, let's look at this cluster. It's one of like the first clusters. So if this cluster kind of separates into two clusters because I I'm just taking off a small ball, right? Then I will introduce these new intercluster edges, right? So this will introduce insertions in the level up. And also I need to delete, to be able to delete one cluster from the parent cluster, and I will also need deletions. So this is sort of like, even if you have a decremental LDD, you don't know how to get a decremental low stress, probabilistic low stress spectrum. Okay. So now, well, you can say, why don't we do the top-down clustering of Bartal? So you can do that. So what does it mean? Okay, first, you still have this probabilistic LDD, right? Initially, you have this clustering into these gray clusters. So now what you do is you recursively compute a tree for each of these clusters, okay? And then you take each of these trees, you connect them to a root vertex, so some auxiliary vertex in the graph, and you connect, how do you connect these trees? So this is the new root node, and this new root node connects to the roots of all these trees that you constructed recursively. And the weight of these edges is proportional to the diameter of the graph, as I said before. So this delta here is the diameter of the graph. Okay, so you can do this, but we couldn't see how to actually control recurse here. And recurse is the propagation of updates among decremental LDDs, because when you have a change, when you have a change in the top LDD, you might actually introduce new changes in the LDDs in the levels below, and we didn't know how to do, how to control recurse. So you can do this. There is an obvious algorithm how to do this in the decremental setting, but we don't know how to actually analyze it. So we take a slightly different approach, which is, I think, more refined, and this is also what solves our problem. So now we view that recursive algorithm as an iterative algorithm. Okay, so what does it mean? So here, initially, I do a low diameter decomposition in the initial cluster. So now previously, you just recursed on all these graphs, okay? So now what I say is that, but this is equivalent to deleting all intercluster edges in the low diameter decomposition, and this gives you these isolated graphs if you delete all these intercluster edges, okay? So for each level now, and you repeat this, so on and so forth. So for each level now, I just maintain a single LDD. So I maintain a single LDD at this level, at this level, at this level, and so on. So the number of LDDs you maintain is proportional to the number of levels in this iterative version of the top-down clustering of Bartal. Okay. So you maintain a okay. So this I explained. So why is this okay? So now when you have deletions here, okay, in this graph, so just propagate them down. But all these decremental LDDs are equipped to deal with these deletions, right? So every deletion that you have here corresponds to a deletion here, okay? And then also when you have cluster splits, you again delete all intercluster edges here. So if it happens that this cluster, for example, separates into two clusters, then you just delete the corresponding baby clusters here and so on. And we also maintain some data structures to ensure that the hierarchy that we get from this approach is indeed a tree. So you maintain a random tree at any point of time. Okay. So this is how we get the decremental PTE algorithm. It's just an iterative version of the top-down graph clustering. Okay, so let me briefly tell you about how do you make this fully dynamic, and then I will try to wrap up pretty quickly. Okay. So first, assume I have a decremental PTE algorithm. So it handles only edge insertions. So what about, edge deletions? What about edge insertions? So I'm claiming that if you have decremental PTE plus, if you know how to do static PTE efficiently, you can get a fully dynamic algorithm. This is the claim. So now assume you have K updates, and K will be chosen later. Now, if I have an edge insertion, I just pass through the decremental PTE, and I know how to do this with stretch log to the 3n. I showed you before, and the height is also bounded, which is actually very important, the depth of this tree. So if if I have an edge insertion, I just keep basically some set I that keeps track of these edges in the graph, okay? And I let, in this case, U be the endpoints of each edges. So I take for every edge, I just take their endpoints and add to the set U. So now this is the algorithm. It's sort of like intuitive, but also interesting. So what you do is you take, you take all paths from these vertices in the set U, from the leaf to the root. And we know that the tree has bounded depth. So this path, the length of this path must be at most log n. So you take the union of all these paths, okay? For example, this graph. And you also look at this auxiliary graph obtained by taking all the union and also adding this inserted edges. These black edges are the inserted edges in the tree, okay? So what you do is take this graph, I union P, which is this graph, and you run a static PTE algorithm of it. So now why can you afford running a static PTE? Because the number of updates is sort of small, like it's K, we haven't set it yet, first. Second, you can also afford that because the depth of the tree is bounded, and actually the length of all these paths is logarithmic, okay? So that's why you can afford running in this sort of like smaller graph, okay? And after you do that, you just you union this TI, so you delete everything, you delete this P, and you replace it with this new tree that you built from scratch P, and also this branch that was left, you put it over here. Okay. So this, so you see the height here doesn't go up by much. So it's still a low depth tree. It goes up by a little, and you can repeat this. And so, okay, so here let's look a bit. Let's have a look at the calculations a bit. So you have this log to the 4n expected stretch, log to the 3 I had before. You get another log n from the static PTE. And if you look at the running time, well, the running time, this is the cost for the decremental PTE, and then you amortize this over k updates because you are building every k updates. And this is the cost for computation, recomputation from scratch, because the size of the graph is of the size k times log n or something. And then if you optimize for k here, if you set k to be m to the 1/2, then you get m to the 1/2 running time. And you can generalize this approach to multiple levels. Actually, the number of levels is going to be bounded by something like square root of log n, and some more technical details to actually make this work in a hierarchical manner. Okay. So I will briefly tell you that just by having dynamic PTE, you actually are solving all pair shortest path problem in a dynamic setting. Why is this the case? It's sufficient just that you maintain log n copies of your dynamic PTEs. Okay. So what you do is that you basically, whenever you get an edge insertion or deletion, you just pass the edge insertion or deletion to each of these data structure TIs, okay? And then upon receiving a query, you compute the shortest path from S to T on each TI. Note that each TI is bounded depth, so computing the shortest path there is easy. It's cheap, logarithmic. And just return the shortest path that attains the minimum value. And you can show that in one of these trees, the shortest path should be go with higher probability. Okay, and then you essentially get the approximation, update time, and query time, which are basically induced, are given to you from the dynamic PTE algorithm. Okay, just to summarize, we give the first fully dynamic algorithm probabilistic T embedding, and we have competitive guarantees on the expected stretch and update time, and we showed how to apply this to all pair shortest path problem and biased network design problem. And some of the future directions here are the following. For example, would like to improve the expected stretch and running time to both being polylogs, say. So we don't know whether you can do that, and sort of like all dynamic algorithms have this problem. We've seen a lot of like subpolynomial factors popping up in many of the problems, and it seems hard to sort of get rid of those because of this hierarchical way of doing things. But yeah, that would be very interesting to see. And also, like, I'm pretty sure that you can apply our dynamic PTE to other optimization problem. We just look at like the most two basic problems in the space. And another very important problem is how to transfer our ideas to the fully dynamic cut-based tree specifier, so maintaining cuts with polylogarithmic guarantees. So Harald Recke gave a talk on this at the DMAP seminar, where he basically showed that you can do something with subpolynomial quality and subpolynomial update time, but we don't know how to get polylogarithmic. So that seems a much harder question, and it would also be interesting to see whether that can be done or not. And I'll stop here. Thanks a lot for listening, and I'm very happy to take any question.
Thanks, Gramoz. I'm applauding on behalf of all the attendees. Thanks for this very nice talk and the quite intuitive insights that you gave along the way. So are there any questions for Gramoz?
I have one question. So consider this problem of getting the stretch down to polylog n, and then look at these two different questions of low stretch spanning trees and this probabilistic tree embeddings. Do you think this will be equally hard on both of them, or one of them will be easier?
You mean in a dynamic setting?
Yeah, in the dynamic setting.
So here we get something polylogarithmic and sublinear, right?
Yeah, so
in this work.
So what I'm asking for is, let's say polylogarithmic stretch and say subpolynomial update time.
Subpolynomial update time.
Yes.
I think the probabilistic tree embedding is easier because if I look at the static static, for example, low stretch spanning tree is still not closed. We don't know whether you can do log n. So being like requiring to be a spanning tree seems to be more restrictive and requires, you know, more difficulties to deal with. So I expect the same thing will appear in the dynamic setting too.
I see.
And also like now we can actually do here polylogarithmic, but we don't know how to do in the low stress spanning tree, and doesn't seem to be easy.
I see.
Even like going, not even just looking at the subpolynomial update time, just going sublinear. So that's my intuition, at least. I don't know, it could be wrong, but yeah.
Any other questions for Gramoz? But we're waiting. I have a quick one. So I probably missed this, but in the when you said when you talked about the dynamic version of the byte bulk network design, and you said that the pairs are also dynamic. So does this mean that this is also both incremental and decremental? So in the sense that, you know, you get a pair and at any given point the set of pairs actually keeps changing, or is it just a prefixed set of pairs that just appears incrementally?
So here so this is, I think, a dynamic algorithm, which is, I would call demand oblivious, right? Because it doesn't require to see the demands in advance. Okay, but any pair of demands that you give me doesn't even have to come from a probability distribution or anything. Any pair of demands that you give me, I'm still competitive in terms of the approximation that I output from this algorithm. So it's kind of a demand oblivious dynamic algorithm. So you don't need to see the pairs in advance. You just have this object, this tree, and then you can receive all of these things online, and I will be able to give you something competitive in terms of the approximation guarantee.
I see. Understood. Thanks.
Sure. Thanks for the question.
Do we have anything else? Well, if not, let's thank Gramoz again for the very nice talk.
Thanks,
Gramoz. So I'm stopping the recording now. So Gramoz, thanks for the nice talk, and we look forward to seeing you soon in the UK.
Yeah, same here.